Okay, I want you to imagine a particle so ghostly, so elusive, it could zip through an entire light year of solid lead and not even notice it was there. Well, those are neutrinos. And right now, billions of them are streaming through your body, through the screen you're looking at, through the entire planet. They are, without a doubt, the ultimate cosmic phantoms.
You know, the poet John Updike just absolutely nailed it with that one. For decades, we pretty much thought they were just these massless messengers, exactly as he described. But here's the twist. We now know they do have mass. It's incredibly tiny, but that tiny fact has absolutely massive implications for our entire universe. Because, spoiler alert, they do. These little cosmic ghosts could be the key to understanding why we exist at all. Why the universe is filled with matter. You know, stars and planets and us, and not just some empty void of energy. But to unlock that secret, we first have to weigh these ghosts. And that brings us to one of the biggest, most exciting puzzles in all of modern physics.
So here's the puzzle. We know there are 3 different types, or flavors, of neutrinos, and they all have slightly different masses. But, and this is the big but, we don't know the order. Is it like 2 light ones and 1 heavy one? That's what scientists call a normal hierarchy. Or is it the other way around? 2 heavy ones and 1 light one, an inverted hierarchy. Figuring this out has kicked off this huge global scientific race, and 2 giant experiments are leading the charge with brilliantly different ways of tackling the problem.
First up, let's talk about the Jiangmen Underground Neutrino Observatory, or JUNO, down in southern China. I want you to think of this thing as a colossal, liquid eyeball, buried deep underground. It's designed to be so ridiculously sensitive that it can catch the single fleeting spark of light that's created when a neutrino finally decides to interact with something. And believe me when I say colossal, I am not kidding. The active target at the heart of JUNO is a 20-kiloton sphere of this special liquid called a scintillator. To give you some perspective, that's about the same weight as 170 blue whales. And it's all just sitting there in this giant acrylic ball, basically waiting for one tiny neutrino to come along and bump into it.
And this is what really sets JUNO apart, its incredible precision. So when a neutrino interaction happens, the liquid flashes. JUNO's sensors are so good they can collect about 1,785 photoelectrons, those are just tiny units of light, for every single unit of energy released. This insanely high light yield means JUNO can measure the energy of that interaction with world-leading accuracy. It sees everything.
But, you know, being deep underground doesn't block out all the cosmic noise. You've got these other, heavier particles called muons constantly raining down on us. To filter those out, JUNO is surrounded by this water-based veto system that's more than 99.9% efficient at catching these unwanted particles. It makes sure that the main detector stays totally pristine, listening only for that whisper-quiet signal from a neutrino. All right, now for our second contender. Half a world away, the proposed India-based Neutrino Observatory, or INO, is planning to take a completely different path with its iron calorimeter, or ICAL. If JUNO is a super-sensitive eyeball, I want you to think of ICAL as a massive cosmic MRI machine. An ICAL is an absolute beast. We're talking about a 50-kiloton detector, not made of liquid, but of solid, magnetized iron. I mean, that's a detector that weighs more than the Eiffel Tower. And it's built not just to see neutrinos, but to actually force the particles they create to reveal their secrets. The way it's built is the key to how it works. It's made of 150 layers of thick iron plates, with these amazing particle detectors sandwiched in between each layer. This design is what lets ICAL track a particle's journey with unbelievable precision, following it step by step, layer by layer, as it flies through the detector.
So there you have it. 2 massive experiments with 2 totally different philosophies. One is using a giant vat of liquid to passively watch for a tiny flash of light. The other is using a mountain of magnetized iron to actively bend a particle's path. So how do these brilliant but completely different methods actually work to solve the exact same cosmic puzzle?
Well, it really just boils down to a fundamental difference in strategy. JUNO is all about light, carefully measuring the brightness and the timing of that little flash a neutrino makes. ICAL, on the other hand, is all about magnetism, using a super powerful magnetic field to see how it affects the particles that neutrinos create.
Okay, so let's walk through JUNO's process. Picture this, a neutrino, probably from a nearby nuclear reactor, zips in and smacks into the liquid. This creates a tiny faint flash of light. That light spreads out and gets picked up by almost 18,000 giant sensors lining the inside of the sphere. By analyzing exactly when and how much light hits each sensor, scientists can reconstruct the event's energy and location with mind-boggling precision.
So how does ICAL do it? It's pretty cool. A neutrino, this one created high up in Earth's atmosphere, smacks into an iron nucleus. This collision creates a charged particle, usually a muon. Now, as this muon zips through those 150 layers of iron, the detector's magnetic field forces its path to curve. And here's the genius part. If it curves one way, it was a particle of matter. If it curves the other way, it was an antiparticle. This ability to tell matter and antimatter apart, that is ICAL's superpower.
So let's put them side by side for a second. You've got JUNO over in China, a 20-kiloton liquid detector using light scintillation, and it's getting up and running. Then you've got the proposal for ICAL in India, a 50-kiloton magnetized iron beast that uses magnetic bending. Two totally different technologies, two different locations, and a kind of complementary race to answer the exact same fundamental question.
And you know what? It is a prize that is absolutely worth chasing, because figuring out the neutrino mass ordering isn't just some abstract academic exercise. No, it's a gateway. It's a key to understanding some of the deepest, most profound mysteries of the cosmos, with implications that stretch way, way beyond the walls of a physics lab. So why does all this matter? I mean, really? Well, because whichever hierarchy turns out to be correct, normal or inverted, it's going to unlock some of the universe's biggest secrets. It could finally tell us if neutrinos are the reason the universe is filled with matter. It might point us to brand new laws of physics, beyond anything we currently know. It will help us understand the insane physics of exploding stars, and it could even give us clues in the hunt for dark matter. Any one of those would be a universe-altering discovery.
When you think about it, these experiments are just an incredible testament to human curiosity. We build these modern-day cathedrals, these immense scientific instruments, and we bury them inside mountains just to listen for the absolute faintest whispers from the cosmos. And as they finally start to listen, you just have to wonder, what other secrets are they about to hear?